All right, so now we're going to move into a different type of physics, right? We've been focusing strictly on mechanics, so like objects moving, um, specifically like solid extended objects moving, but now we're going to move into discussing fluids. The next lecture will be fluid motion. We're going to talk a little bit about solids, solid deformation, stuff like this. So, topic of the lecture, solids and fluids, but mostly fluids. So, we have not looked at the deformation of our solid objects, but whenever an external force is applied to a solid, it can cause deformation of the solid structure. So we kind of mentioned deformation a little bit whenever we were talking about momentum and inelastic collisions, how sometimes the energy can be transferred into deformation. So we're going to look at specific types of deformation. So a large force will cause a permanent deformation due to the breaking of bonds between atoms within the solid. So whenever we think about like a permanent deformation, we can think about a spring, right? If you stretch a spring hard enough, you're permanently going to deform the shape of that object. If you really want to, you could turn it into just a straight wire, right? So to discuss deformation, we need to think about something called the stress that is put on the material. So stress is just our force per unit of area. How much force are we applying over a specific area? And strain is going to be a measure of the degree of deformation. So how much has the object changed shape in comparison to its original size? So when we're looking at deformation, we're going to look at three specific kinds. We're going to look at a pulling or a stretching, and this is going to be Young's modulus. We'll also look at like a bending or a shearing, and this is the shear modulus, and then we'll think about like squeezing an object, which is the bulk modulus. So Young's modulus tells us how easy it will be to deform the material through tensile stress, right? So just tension, pulling and stretching a material. So our equation for this is that our tensile stress, right, our force per unit of area is equal to Young's modulus. Now, these moduli are specific to different materials, kind of like as a spring has a specific spring constant. Our materials will have a specific Young's modulus to them, and it represents how hard or how easy it will be to pull or stretch that material. And then we multiply that times the tensile strain, or how much the object has changed in size compared to its original size. So when we look at a material and we stretch that material has an elastic limit, right? So this is how far you can stretch a material before it is permanently deformed and before it actually breaks. So we can see that there is elastic behavior that happens. Then at some point in time, it becomes permanently deformed, and then the object breaks. So this permanent deformation happens at the elastic limit here, and then it will eventually hit a breaking point. What about shear modulus? So this is the type of deformation that occurs when an object is subjected to a force that is parallel to one of its faces. So I think that this little GIF is a great example of a shearing, right? So it's kind of like a bending to the side of a solid object. Now, don't think like Jello, right? Because if I do this to Jello, it's just going to bounce back. Think about something solid like a metal, right? A shear of metal. And the form is almost exactly the same, right? Except for instead of Young's modulus, we now have a shear modulus. And instead of the change in length over the original length, we have this delta x, right? So how much it has changed in the x direction divided by the height of the object. So a material that has a large shear modulus is going to be difficult to like bend. And then we have the bulk modulus, right? So volume stress, right? This is just going to be pressure is equal to negative the bulk modulus times the change in volume divided by the original volume. So a material that has a large bulk modulus is not going to compress very easily, while if we have a material that has a very small bulk modulus, we can compress it really easy. Think about like a stress ball has a very small bulk modulus, but like a steel ball has a very large bulk modulus. So different states of matter, right? And these are more like definitions of different states of matter. I assume most people know like solids, liquids, and gases, but a solid, right, has a stable, definite shape and has a definite volume. So solids can only change their shape when an outside force is applied or when it has been like broken or cut. A liquid is different because it is nearly incompressible. It is a fluid that conforms to the shape of its container, but retains almost a constant volume independent of pressure. This means that it's non-compressible. And then a gas is a compressible fluid. So notice that fluid and liquid are not interchangeable terms. Liquid is incompressible. Gases are still fluids, but they are compressible. So not only will a gas conform to the shape of its container, but it will also expand to fill the container. And then there's plasmas, but we don't talk about plasma in this class. So fluids, both liquids and gases, are easily deformed by external forces, meaning like I can change its shape very easily. So in many situations, we can think of liquids as uncompressible and having a fixed volume, whereas gases are easily compressed and expand to fill containers. Both are fluids. So in order to talk about fluids, we need to define what pressure is. So a static fluid does not flow. It is at rest everywhere. And so when we are talking in this specific lecture about the study of fluids, we are talking specifically about hydrostatics, right? So fluid that is not in motion, fluid that is at rest everywhere. And in a static fluid, I think it's important to note that the atoms or molecules are not static themselves. They are moving, they're bouncing around, but the overall fluid itself, like macroscopically, is not in motion. Microscopically, on the molecular level, they're bouncing around, they're moving, they have energy, they have collisions occurring, but macroscopically, no motion, stationary, it is not flowing. It is like your glass of water sitting on a table. So, fluid pressure is actually caused by collisions of these atoms or molecules, right? So pressure is equal to force divided by area. You maybe put that together based off of our discussion of force over area and how whenever we went into a bulk modulus, I changed that to pressure, right? So imagine a tiny surface, and at various points within the fluid, we think about what is the force of the molecules of this fluid hitting that tiny surface, and what is the area of that surface. And if we calculate the total force over the area, we get pressure. And pressure has units of pascals. Sometimes you will need to use atmospheric pressure, right? If something is open to the atmosphere, and that is 1.013 times 10 to the fifth pascals, or 1 atm. So there are certain requirements for determining when a fluid is at rest in a container. Number one, probably the most obvious, all portions of the fluid must be in static equilibrium, aka no portions of the fluid can be flowing. Two, all points at the same depth must have the same pressure, meaning this little guy is in the pool. If he was over here, he would feel the same pressure as if he was right here, as if he was right here. Now, when he sinks down to the bottom, the pressure that he feels changes because of the amount of water that is on top of him. But if he moves just like translating back and forth on the x plane, he will feel the same amount of pressure as long as his depth remains the same. So one thing that we can think about is, what would happen if these two conditions were not met? What would happen if this little guy has a different pressure on one side than he does on the other side? Well, this difference in pressure would cause a net force to occur, and he would be moving. So he would no longer be in equilibrium, right? So when a fluid is at rest or static, the pressure increases with depth because the weight of the fluid above it adds to the force that is exerted on the object. So the further this guy goes in the pool, the more force he feels pushing down on him because of the weight of the fluid above. So Pascal's principle tells us that when pressure is applied to a confined fluid, that pressure is transmitted equally in all directions throughout the fluid, meaning that the pressure that is applied to the left side of this container has to appear on the right side of the container as well, right? So this is how hydraulic systems function, and it's because our fluid is incompressible. So if I push down on one side, water has to go up on the other side and vice versa. So pressure 1 has to equal pressure 2, meaning that force 1 divided by area 1 has to equal force 2 divided by area 2. So we see here that area 1 is much smaller than area 2. So I had to push down further to get this hydraulic lift to go up just a little bit. And that's because smaller area, larger area, but the total pressure has to be the same. Density is a characteristic property of a material, and it depends on two things. One, the size of the atoms in the material, right? So larger atoms take up more volume, smaller atoms take up less volume, and the spacing of the atoms in the material. So if I space them out really, really far, they take up more volume. If I condense them and squish them down, they take up less volume. So density is equal to the mass divided by the volume. So I can have the same atoms, but have them taking up more space or less space and change the density of an object. I'm changing the density of the object because this volume is changing. So this is the Greek letter rho. It looks like a lowercase p, but notice how I have these fancy tails here. That's because this is the Greek letter rho, not the letter p. We're going to have equations that have a capital P for pressure and a rho for density, and I want you to make sure that when you write these things out, you can clearly see the difference between your P for pressure and your rho for density so that you don't get these things confused. So let's say I hand you 5 grams of aluminum and 5 grams of gold. Which one would have a larger volume? Okay, well, aluminum has a density of 2.7 times 10 to the third, and gold has a density of 19.3 times 10 to the third. So aluminum would have more volume than gold because it has a lower density. Don't believe me? Write out rho is equal to mass divided by volume. Plug this in for rho, switch out the masses for 5 grams, and ta-da. So more mass in less space is equal to greater density. So the density of a subject measures essentially like the compactness of the substance. How compact is this? So what happens when we put things in water? Well, it kind of depends based on the density of my object and the density of my fluid, right? So here in this little jiffy, they got 3 different objects and 3 different fluids. Oh, I guess it's 4 objects and 3 different fluids with different densities, right? So sometimes objects float like ice cubes, and sometimes objects sink like rocks. And this occurs because of the differing densities in the objects, as well as what we see here, the differing densities of the fluid. So that brown fluid is more dense than that grape. And the blue fluid is more dense than that bottle cap, right? So we get this buoyancy. So Archimedes' principle tells us that any object that is fully or partially submerged in a fluid is buoyed up with a force that is Oh, I phrased that weird. Any object that is fully or partially submerged in a fluid is buoyed up by a force with a magnitude equal to the weight of the displaced fluid. So this is our definition for buoyant force, and it is equal to the density of the fluid times the volume of the fluid that has been displaced times g. So one of the biggest mistakes I see is that students assume that the volume is the volume of the object. That is not the case. So this, I think, is a great example. The volume of this wood block is not equal to the volume of fluid that has been displaced because this wood block is floating. Now, if I push the wood block and it was more dense and it sunk down, then the volume of fluid displaced would be equal to the volume of my wood block. But because part of this block is sticking out of the top of the liquid, the volume of fluid displaced is not the same as the volume of the object. So our buoyant force is fully dependent on the fluid, not the object. So ways that we can determine the density of an object is to look at the specific gravity. So we can measure the density of a substance compared to the density of water. And they do this all the time, like at the urologist, or whenever you have to pee in a cup, it'll say like, this is the specific gravity of your urine, right? So it can help them look at things like kidney functioning. It shows how many particles are in a person's urine in comparison to water. So if you have low specific gravity, you're really hydrated. And if you have a high specific gravity, you could be dehydrated, or there could be other things going on, like sugar or protein in the urine, and that's why they want you to pee in a cup so that they can look at this and try to catch things ahead of time. But we can determine the density of a substance by looking at the specific gravity. So the next equation that we need to think about is something called hydrostatic equilibrium, or our equation of hydrostatic equilibrium. And this is something that we use whenever we want to determine the pressure at a specific location. So imagine that I want to calculate pressure that is being applied to the head of this little guy meditating at the bottom of the pool. Well, I need to consider the atmospheric pressure above him and the pressure that is due to all of the weight of this fluid above him. So our pressure at point 2 would be here, is equal to pressure 1, right, the pressure at the top, plus the density of the fluid times g times the distance between the top of the fluid and the top of this guy's head, right? So if we have an open container, P1 will always be atmospheric pressure. So if I look here, right, and I want to figure out what is the pressure at this location, well, this is slightly more complicated because I have multiple open containers. But the difference, my y1 minus y2 is my difference in the y direction between the top of this fluid and the point that I'm looking at. So an example of this would be like an IV bag, right? So the higher the IV bag, the greater the pressure that is coming out the end of the tube and the faster the fluid flows. So if the bag is too low, the pressure may not be sufficient enough to overcome venous pressure and the flow could stop, meaning like your saline solution is not getting into the patient. If it's too high, fluid flow may be too quick and cause discomfort, or real worst case scenario, you blow out somebody's veins. So the pressure from the fluid weight must match or slightly exceed the pressure in the patient's vein for this fluid to enter smoothly. Now, obviously, in medical settings, they are not relying on you to sit there and calculate how high does this IV bag need to be, right? They have roller clamps, they have the drip chamber to help account for this. But this is an example of hydrostatic equilibrium. The last thing I want to mention is something called gauge pressure. Some problems will ask for gauge pressure, and gauge pressure is just the difference in pressure,